The next speaker is Catherine Powell. Catherine Powell is also one of the organizers of the special program semester, and she's a reader at the University of Manchester in applied mathematics and numerical analysis. Catherine is also part of the group of uncertainty quantification and data science in the University of Manchester, and her research topics are related with uncertainty quantification, data science, as well as numerical analysis. And today she's delivering a talk on reduced basis solvers for stochastic Galerkin finite element matrix equations.
Okay, thank you very much. Can everybody hear me? Sound okay? Okay, so this is going to be a linear algebra talk. This is going to be a talk about how to design a low-dimensional approximation space for the iterative solution of some special linear systems of equations that we get when we apply these methods that are known as Stochastic Galerkin finite element methods, so I might say SGFM for short, when we're solving PDE models with uncertain parameters. So first half of my talk will be fairly introductory, I hope. So if anybody wants to stop me and ask any questions, that's totally fine. I prefer to be understood and not get to the end than not to be understood at all. In the second half of my talk, I'm going to talk about a very specific method. It's quite old now. We did this a couple of years ago, and it was very much motivated by my collaborator, Valerio Simoncini. So the results I'll show you towards the end were joint work with Valerio Simoncini, who's well known in the linear algebra community, and David Sylvester, who's a colleague at the University of Manchester. And also towards the end, I'll show some more recent numerical results that were produced by Craig Newsom, who's over there. He's a PhD student at the University of Manchester, and he gave a poster earlier in the week where he was talking about reduced basis methods in a slightly different setting for use with sampling methods. I'm going to talk about reduced basis methods in a different setting. Okay, so the first few slides are supposed to just put all of this in some context to try and explain what I'm doing and why I'm trying to do it. So I'm interested, like many of the talks we've already seen this week, in solving PDE problems. So here's my generic PDE problem. So this is to explain the notation. So I have a differential operator L here, or a collection of differential operators, and somewhere inside that I have some coefficients probably that depend on a set of parameters. So in Peter's talk just now, his y was a xi. Now I've gone from xi to y. So in here I've got some parameters. So y is going to be my vector of parameters. So y will have m components. So there'll be m parameters, and y will take its values in some set gamma, which I'll call the parameter domain. But my solution to my PDE is also going to be spatially varying as well. So x will denote my spatial coordinates. So I'm looking for a solution, u, right? This is my continuous model. This is something I can never compute, of course, but that's the object I'm interested in. It's a solution of both x and y. So what am I going to assume? I think it's important while you tell somebody about a new method that you've invented that you say what it is good for, but also what it is not good for. It's good for this, right? If your problem doesn't fit in this category, you shouldn't use this method. Right? So I'm going to assume that the parameters in this problem, that I know what m is. Okay? I'm also going to assume that m is not that large. So m is in the order of 10, 20. I'm also going to assume I know what the distribution of these parameters is. Uniform, Gaussian, whatever is appropriate for the problem, provided that this problem can be shown to have a solution that exists, is unique, etc. And crucially, many people have used this during their talks this week. I'm going to assume that this differential operator in here depends linearly on the parameters. So I'm going to have examples where the differential operator can be decomposed in this way. I'm going to have a leading part of my operator which doesn't depend on any of the parameters, and then the rest of it can be written as a sum of other operators, and in here I have my parameters. Okay? So that is the setting that I'm working in. We'll see several examples. And what's my goal? What am I trying to do? I'm trying to approximate this thing that I can't compute, both as a function of x and as a function of y. And I'm not going to do any sampling. Okay? So I'm looking for a functional approximation of this thing, both as a function of x and as a function of y. And the particular strategy that I'm going to use to build my approximation is called Galerkin approximation. We've seen it in several talks in the applied math community this week. So I'm interested in generating an approximation. I'll call that u hat in some space, which I'll call v hat. And this approximation will be generated by solving a weak form of that problem. So typically what we're going to do is stick u hat in here, multiply both sides by a test function, and integrate. And when I say integrate, we'll have an integration both over the spatial domain and over the parameter domain as well. So if you're in the statistics community, if you've never seen this, you don't really need to worry about this. All you really need to know for the purposes of this talk is when we look for an approximation which has this property, that it satisfies Galerkin conditions like this, what we have to do, the work that we have to do in order to get this approximation is to solve a linear system of equations. So ultimately when you do this on a computer, it's just a matrix problem. Just a matrix problem. But the key thing, this is typically the bottleneck in your computations if you want to generate your approximation this way. You could also view this as a problem in design. Design is a word that I've learned that statisticians use a lot. For us, how do you design the approximation space? Right? Not points in the parameters. I mean, how do you design the best space here? Okay, because ultimately we'd like the error between u and u hat to be as small as possible. Okay, so we could design this space in such a way that this is a very small matrix problem, or it might be a very large matrix problem, and it would be really good if we could choose this space so that this matrix happened to be diagonal. That would be brilliant. We can all solve a diagonal system, but unfortunately what falls out here, whether or not we've put a lot of effort into designing this space well or not, is usually some complicated linear system of equations that we need to solve. And we need to worry about this. Okay, so here's what's done as what I'll call a standard approach. Some might say naive approach. So how are we going to design our approximation space? So the standard way to do this is to take two spaces. One I'll call x and one I'll call p. Remember, our solution, the thing that we're trying to approximate, is a function of our spatial coordinates and our parameters. So there'll be two components to our approximation space. On the one hand, I'll have a space x, which will be associated with my spatial domain, and I'm going to use finite element approximation. So I have a mesh on my computational domain and a set of basis functions that are defined with respect to that mesh. So I have a space x, which will have dimension nx, and then I have another approximation space, which I'll call P, and for the purpose of this talk, P will be a set of polynomials. So I'm going to choose some polynomials psi, and I'm not going to be prescriptive in terms of what that polynomial space is. We can design it in quite a flexible way. Typically, this is the kind of notation we use. So remember I said the number of parameters is fixed, so what we can do is take a set, which I'll call JP, of multi-indices, or vectors if you want to think of them like vectors. Take a set of vectors with m components. The components in these vectors give me polynomial degrees, and basically each polynomial in here is a product of one-dimensional polynomials that have these individual degrees. So by choosing these multi-indices in a smart way, I can design a polynomial space with basis functions which are multivariate polynomials, and ideally we'd like these to be orthonormal polynomials. Okay? So we choose a set x, we choose a set p. These are functions of the spatial coordinates, these are functions of the parameters, and we form the tensor product. We form the tensor product, we write down our Galerkin equations, we get a linear system to solve. What does that get us in the end, you might be thinking? So if we can solve this linear system, we get a vector. That vector gets us a set of coefficients that represents a function. So ultimately this is our approximation. So we can write it as a linear combination over all of these multi-indices. So it's a linear combination of polynomials in our parameters at the end of the day. So having talked with statisticians, I know that many people are more familiar with the term intrusive polynomial chaos approximation. It's intrusive because I have to solve a linear system of equations to get the coefficients that go in this approximation. So these coefficients are not computed by doing projection and sampling or quadrature or fitting. They are obtained by solving the Galerkin equations. Okay? So some of you may know this paper that Tony O'Hagan wrote. It was a statistician's criticism of polynomial chaos approximation. And in it there are some interesting comments about the intrusive version of polynomial chaos. Okay? So I hope I can at least convince a few of you that for certain problems, intrusive is okay, right? That's if I achieve nothing else, I hope I achieve that. Okay? So if you're a statistician, you might also be thinking, well, what can I do with this once I've got it? Well, once you've got this is a function of your parameters, so if you needed to use this as a surrogate, you needed to do sampling, you could sample from this very cheaply if you want to. You could use this in some other loop of your UQ algorithm if you wanted to. I'm not going to focus on its use as a surrogate. All I'm really interested in is how do I get this cheaply and quickly. Okay, so I put this slide in after listening to some comments earlier in the week. Ideally, from a numerical analyst perspective, we'd really like to do this. Okay? If I just start with A space X and A space P and just worry about the linear algebra, I could be missing a big point that these spaces might not actually be any good. And so personally, I think if you can do this, this is what you should do. Ideally, right, with no a priori knowledge about what's the best choice of the space to use, what we'd really like to do is adaptivity. Right? We'd like to start in low-dimensional versions of these spaces. We'd like to compute an initial approximation. We'd like to be able to estimate the error associated with that approximation. Right? Remember, the true error is something we can never compute, but we can, and this is a big branch of numerical analysis, estimate the error in the current approximation a posteriori in a computable, efficient way without knowing what the true solution is. Okay? If our estimated error is small enough, we stop. If not, we need to go and somehow improve our design of these spaces. We need to enrich these spaces, augment them somehow. So if your error estimation strategy is informative, you'll get some additional information when you compute it about what a good strategy for enriching those spaces is. And then you keep doing this adaptively until, in the last step, you have spaces which are sufficiently well designed that at the last step, your error, your estimated error, is smaller than the tolerance that you want to ensure in your computations. Okay, so this all relies on you having a good, efficient, very accurate a posteriori error estimator. So I talked about how to do this in workshop 2. So the slides for that talk are available. Martin Eigel also talked about how to do this in workshop 2 as well. The strategies that we use to do the a posteriori error estimation are very different, but if you're interested in this, I would invite you to go to the workshop website and look at the slides for those talks. This is just one slide that I also showed in that talk. This is a workshop this week about sort of dimension reduction. Of course, a key thing that we want to know here is, especially when we're designing the parametric part of our approximation space, how many parameters, right? So I said in my original slide that I'm going to assume the number of parameters is fixed, but actually we might not know how many parameters are important to represent in our solution. So should we reduce the dimension of the input space before we build the surrogate? That's essentially what I'm going to do today, but if we actually take this approach, then if we can do the error estimation in the right way, we can also learn as we're going along which parameters are important to represent in our approximation as well. So we don't necessarily need to reduce the dimension of the input space before we start. So I can actually start, this is everyone's favorite elliptic PDE, I can actually start from a coefficient in my PDE which depends on infinitely many parameters. So here's just an example. This is a very synthetic example. So I have a sort of a random input, infinitely many parameters. I've got coefficient functions here which decay at a certain rate. Right? So I picked a certain rate because I know what is the optimal achievable convergence rate to approximate the solution. And the algorithm just takes in a tolerance from me. That's all I give it. Right? I say I want to design my approximation space and deliver an approximation such that the error between the true unknown solution and the thing I computed is guaranteed to be below this tolerance. Okay? The algorithm runs, it designs an approximation space. In this case, it happened to design an approximation space of this size, and this includes both the spatial degrees of freedom, the parameters, and which polynomials in those parameters to include in the approximation space. And even though the continuous problem had a solution that depended on infinitely many parameters, the algorithm learned that only 10 of those parameters needed to be represented in the approximation space to deliver me an approximation that got me the accuracy that I asked of it. Okay, so we can do things like that. And if you want to read about that, so I'll make my slides available. So there's lots of work in this area. If you want the references, you can read them. Okay, so that's just sort of the warm-up. So what I'm going to do then is I'm going to focus very much now on just solving this linear system of equations. Okay, I'm going to assume I've designed my space. I've got an x, I've got a p, I now need to solve the linear system of equations that's associated with a space that I've chosen. Okay, I'm going to talk, first of all, I'll just give you a few examples, different PDEs, and I'll just show you just on one slide just what is the structure of these matrices. This might look a little horrible if you don't like linear algebra. I know there's a sub-community of people here who really like linear algebra, and perhaps there are some people that don't. If nothing else from those slides, perhaps you just visually see the structure in all of these problems. Right? I'll talk about how we rewrite the problem as a matrix equation, and then my last few slides are about this very specific method that we use. We call it multi-RB, so RB means reduced basis, and I'll explain what the multi is later on. And if you get nothing else from the talk, the message I want to leave you with is we can only do this if the solution really has a low rank and we can exploit it, and our algorithm, we claim, is memory efficient. Okay? Okay, so part one then. So what is the structure of the linear systems that we get when we apply these stochastic Galerkin finite element methods? So typically we get matrices that have this kind of structure. So someone earlier in the week color-coded their slides exactly like this. I think it was Sergey. I'm not sure. I can't remember if this was red and this was blue or it was the other way around, but this is the way I usually do it. The coefficient matrix A is usually expressible as the sum over m. M is the number of parameters in your problem, or the number of parameters that's currently active if you're in a sort of outer iterative adaptive loop. Sum of Kronecker products of matrices that come from these two different components of the approximation space. Why does it have this structure? Remember the assumptions that I made, that my approximation space is a tensor product space, and the other key assumption is that the differential operator depends linearly on the problem parameters. Those two assumptions mean that this is why we get this structure. Problem is, and this is why people get upset about intrusive methods, is that the dimension, the number of equations I have, is the product of the dimensions of my individual spaces. So at first glance this might seem like it's just impossible. So what does the color coding mean? The matrices on the left here are matrices that are associated with the X space that we've chosen. That'll be the thing that's determined by our choice of the spatial discretization. We'll get those from existing code with not much effort. And then the extra thing that you'll need, if you're doing this rather than, say, doing a sampling method, you'll need these matrices G, which are in red, which are associated with the polynomial part of the approximation space. And if we chose the usual polynomial chaos type basis functions, which are orthonormal, then in particular this matrix G0 will be the identity matrix, and the other ones will be very sparse as well. So we know that. Those people who work in this area love these matrices. We pretty much know everything about them. We get quite excited about them, or at least some of us do. So here's the first example, right? So I'm just going to show you now a few examples of problems which give rise to matrices which have this structure. So everyone's favorite elliptic PDE. So if the coefficient in here has a structure like this, depending linearly on a set of parameters, we definitely get a system matrix which has this form. So what's special about elliptic PDEs? You know, statisticians have repeatedly asked me this question, why elliptic PDEs? Well, nothing so special about this. The thing that's special in terms of the linear algebra is that this matrix always turns out to be symmetric and positive definite. Right? That's what happens if it happens to be an elliptic PDE. We also know that these other K matrices, for example, should be symmetric, unless you've done something a bit crazy. And we know various other things about the component matrices. So whatever this PDE operator is, its features will then sort of be imposed on the matrices. Right? They'll inherit characteristics of the original PDE operator. Let's take something else. Navier-Stokes equations. This is a nonlinear problem. So the viscosity here, so let's say we don't know the viscosity. We want to model the viscosity as a function of a parameter, right, with a particular mean, particular standard deviation. Then the solution, so now I've got two solution fields, P, pressure, U, velocity. So now we're treating these solution fields as functions of this parameter. So what can we do? Can we apply stochastic Galerkin finite element method? Well, yes, we can, but we need to linearize the problem first. So after linearization, at each step of the linearization, we can apply the stochastic Galerkin finite element method, but this time we get a system matrix which looks a lot more horrible. But I hope you can at least see, okay, it's got a block structure, we've got Kronecker products again, we've got sums again. Again, I'm just seeing the same structure repeated and repeated. Sums of Kronecker products of matrices. The only difference here is these matrices are non-symmetric. So we have the same kind of structure, but some particular different features which change each time you encounter a different PDE operator. So here's a time-dependent heat equation. So you've seen this in Martin Stoll's slides yesterday. So we might have a coefficient in here, a diffusion coefficient, which again depends linearly on a set of parameters. So this problem also fits into this class that I talked about on the first slide. So we can apply the stochastic Galerkin approach. If we do that, we get a system of ODEs. We then have to discretize in time, of course, as well. And then we have to solve a sequence of problems. But at each step, we'll be solving a matrix problem where the matrix has terms that look like these same things that we've seen over and over again now. Okay? So sums of Kronecker products of matrices. So that's what we want to do. We want to do good linear algebra. We want to be able to solve fast, efficiently, linear systems of equations with coefficient matrices that look like this, or at least have blocks which look like this. Okay? So how can we do this? So these things are massive, billions of equations. Right? And I'm going to show you I can solve billions of equations. The golden rule, of course, is you never ever assemble this matrix. Just because I've written it down as A does not mean you have to write a computer code to assemble A. You should never try and do that. You don't even need to assemble the G's and the K's. You just need some information about them. Right? You need their non-zero entries, for instance. So you should definitely forget about direct solvers. So in those of us who do MATLAB, we know backslash. Those of you who do what is it? Backsolve something? Backsolve. Don't do backsolve. Don't do backslash. Forget about that. Don't do Cholesky factorization. Don't do any form of factorization. We need to do something else. So can we solve systems with coefficient matrices that look like this using standard iterative methods? Right? So forget about direct solvers, but can we go to an iterative method? Well, people who work in linear algebra are saying this is all obvious. For others, it might be less obvious. When we do standard iterative methods, all we ever need to do is multiplications with A. Solving a linear system of equations typically does not mean you have to invert anything. We just need to do fast multiplications, the action of this in a multiplication on a vector. We might need preconditioning. If this is very ill-conditioned, we'll need something to accelerate the iteration. That's a whole other story, which I won't get into today. But the key thing is, if you're going to use the standard iterative method, you will need enough memory to store a vector of length nx times np. Because that's what your solution is. It's a vector of length nx times p. This is the size of your spatial discretization space. This is the size of your parametric approximation space, if I can call it that. If you can't store a vector of that length in your memory, you definitely can't use a standard iterative method. So what do I mean when I say standard iterative method? And again, to those people who do linear algebra, this will be completely obvious, but to others of you, perhaps not. So standard iterative methods, if you are a user of black box codes, if you can look into your code, you might see names that look like this. PCG, MinRes, GMRes, BiCG stab, QMR. These are all standard iterative methods, which are all used in different circumstances. So for example, if you use symmetric positive definite systems, then this is probably something that you use. If it's symmetric and indefinite, this is probably something that you use. So what does a standard iterative method that belongs to one of these classes look like? So typically we call them Krylov methods. And the idea in a Krylov iteration method is you start off with an initial guess for the solution of your linear system. And then at each stage of the iteration, you're essentially constructing an approximation space. And at each step of the iteration, a new basis vector gets added to that approximation space. Okay? And typically, the basis vectors that get added are formed by doing matrix multiplication with a vector. Okay? So we'd start on iteration 1 or 2 with one basis vector, which I'll call V0. At the next iteration, a new vector gets added to the approximation space, which is A times the previous vector. At the next one, it's A times the previous vector, and so on. So this is called a Krylov space, right? This is not what all of these methods do, but the simplest Krylov space can be thought of in this way. And at the end of the iteration, what you have is a vector that approximates the solution to your problem that's a linear combination of these basis vectors. So this is what's behind the scenes of many of these methods. An approximation space is being generated, although you just do not see it. Okay, so what's wrong? So let's take the elliptic PDE. Let's take a diffusion coefficient, which has the structure that we said that we needed. It's got 20 terms here. So let's just do something crazy. Let's just take a very fine finite element space. So X has got dimension 65,000 and something. I've got 20 parameters. Each line here corresponds to a different parametric approximation space. So when the dimension of P is quite small, no problem. The product of these two numbers is okay. I can solve the problem in 6 iterations with a very standard iterative method in a minute or so. Not a problem. But then when we get into a scenario where the dimension of P is 10,000 and something, multiply these two things together, I just can't do anything with a standard iterative method. Okay, so this has sort of spurred on a lot of research in linear algebra community. We simply can't use these black box iterative methods, so we need to do something different. Okay, so here's what the algorithm I'm going to present does. You could think about it as an adaptive algorithm, but here, unlike the slide that I wrote down earlier, I'm just assuming here we've been given these spaces. Okay? So I've been given these spaces and I just need to solve the problem, the discrete problem associated with those spaces. And I may be given spaces that are probably too large for what I want to actually compute in terms of reliability or guaranteeing accuracy. But I'm just going to assume X and P have been given. We've got the corresponding matrix problem. So instead of viewing the solution as a long vector of coefficients, I'm going to reshape that vector into a matrix. So I'm going to view the solution object as a matrix rather than as a vector. And then we have an iterative algorithm that generates a sequence of approximations, which I'll call UK. So at each iteration, this will be the form that the approximation takes. It will have two factors, a VK and a YK. Will never ever form the product, that's the key rule. So VK will have this dimension. Remember, NX is the size of X. It will be NX times NR. YK will be NR times NP. So the product of these two things has the dimension of what we need, but individually they'll be much smaller. So if NR is much smaller than NX, this will be what Martin called a tall and skinny matrix, and this will be a short and fat matrix. So this will be a matrix with very few columns. This will be a matrix with very few rows. Key thing I want to stress is we are not going to impose what NR should be before we start. We're just going to run this with a tolerance and let it run until NR is big enough that I meet this tolerance. But in terms of the whole story, what I'm doing here is only controlling the accuracy between the discrete solution and my approximation to the discrete solution. This is not controlling the accuracy between my discrete solution and my continuous PDE. That's all tied up in how I choose this space as X and P. But we need to balance both at the end of the day. Okay? So this is what I'm going to do. So we have to be able to design those two factors, the V and the Y. So the starting point then is to forget about thinking about a linear system, AU is equal to F, with a solution which is just a very, very long vector that we can't store. So at least as a thought experiment, let's think about reshaping that vector into a matrix. So this is now going to be my solution matrix. It's got dimension NX times NP. Right? So each column is associated with each polynomial in my basis. Right? So these are not snapshots or anything like that. This is like the spectral representation of my solution, one per polynomial. If I reshape the right-hand side vector in the same way, I rewrite my linear system like this. And this is called a matrix equation, a multi-term matrix equation. The linear system has a solution which is a vector. A matrix equation has a solution which is a matrix. Okay? So the thing is that U is often a low-rank matrix. That's why we can get away with approximations that have this form. It's not always such low rank, I have to say. If people are showing you results where the ranks are always very small, it's because the problem is very special. They're not always low rank. But the key thing is that the rank So these kinds of problems we're talking about here is typically independent of the finite element spatial discretization. Right? But it will be linked to other properties of the PDE operator. Okay, so at this point there's probably a lot of you in the room thinking, oh, I've worked on this. Yes, lots of people have worked on this kind of thing. So I just want to acknowledge that. Research in this area goes back at least a decade. You've heard from some of these people already this week, and you'll hear about some others later today as well. So I've got the next 3 slides. I've got lots of references. If you want to go and see what other people have done in the literature, you can read these at your leisure and find out more. So Anthony Nui, who's going to talk a little bit later, did a lot of work in this area. Herman Mattis, who visited earlier in the program, he's also done some work in this area. Sergei Dolgov, who you've already heard from, Martin Stoll, who you've already heard from, Howard Ellman, and Kukchian Lee have done some work very recently. There's just lots of work in this area, right, exploiting the low-rank feature of the solution. And then there's also this big field in tensor methods as well. I'm not going to talk about tensor methods. I just want to highlight Lars Grasevic, who you've already heard from, and again Sergei Dolgov and others as well. Herman Mattis again over here. There's lots and lots of work in this area. Okay? Okay, so what do we do then? So here's my matrix problem now, right? So the solution is now a matrix rather than a vector. So the algorithm that I'm going to talk about, we need to do some pre-processing first. And I want to stress that this isn't actually explicitly done. This is just done implicitly within the algorithm that I'm going to present. As it's given to us in this way, if these matrices K that are over here are coming from a standard method like a finite element method, they'll be very ill-conditioned with respect to the finite element mesh parameters. So we want to get rid of that. So the first thing we're going to do is sort of a preconditioning step. Okay? So you may or may not remember, I told you that G0 is usually the identity matrix, so that's good. What about K0 over here? K0 will be a finite element matrix. So if this is an elliptic PDE, for instance, this will be a symmetric and positive definite matrix, so it will definitely have a Cholesky factorization. So I've learned that if nothing else, Cholesky factorization is used both in statistics and it's used in applied mathematics as well. Right? So I think we all know what that means. So we could factorize this matrix, and then I introduce a new solution variable x, which is L transpose times u. So I'm going to reformulate my problem so that I solve for x instead of u, and then I can obtain u once I've got x. And then I'll hit both sides of the equation with L inverse, and then what I have is a new matrix problem. And the matrices on the left now are much better conditioned than they were before. Although, just to stress, I do not ever construct this matrix. Do not. At some point in my algorithm, I will need to do solves with L, but that's it. I do not construct these matrices. The other thing I'm now going to do, right, these matrices that they have here, we'd like to know something about their eigenvalues, and we'd like to shift them so that their eigenvalues are in a convenient interval, which we can then work with. So what I'm going to do here is I'm going to introduce some shifts. So if you just look at this term here and compare with this term in the brackets down here, you'll see that I've added on an alpha m times I. Alpha m is a parameter, but this is not like a nugget term or a fiddle factor, as I call it. I'm going to add it on, but I'm going to take it out again. So these equations are exactly the same. Right? So I've added on something, but I've taken it out again. I've done that so that the matrices I end up with here have eigenvalues which lie in a convenient interval, in particular in the real, well, we want the real parts of the eigenvalues to be in the positive reals. That's what we want. When we've done that, we have sort of what I call a reformulated or a pre-processed matrix equation. The advantage of this pre-processing, if we can do this, is that the matrices that we have on the left now are much better conditioned with respect to the discretization parameters. That's why it's been done. And with the shifts, we also know that their eigenvalues are in a nice interval as well. But I haven't done any reduction yet. None at all. Right? So there's still a big problem. So here's where the reduction comes in a slide. So what we need are NR vectors, right? Hopefully NR is much less than the size of my finite element space. I'm going to collect those vectors together into a matrix which I'll call V. These vectors, unlike reduced basis methods that are used in the sampling context, are not snapshots. They're not model runs. Okay? These are not different outputs of a simulator for different choices of the input parameters. That's not what they are. I'll tell you how we construct them in a little bit. I'm going to approximate my solution by this form. So v times y. So what does this mean? I'm going to generate an approximation, a matrix, and each column of this matrix will be a linear combination of these basis vectors. That's what it means. How do I find which linear combination? I've got to find this back to y. So y will have this dimension. How do I find it? I find it by imposing a Galerkin condition as well. Right? So I take this, I plug it back into my matrix equation, I find the residual by subtracting, and force the residual error to be orthogonal to the columns of this matrix. This is typically done in reduced basis methods, but what comes out for us is a new matrix equation which has this form, and now you see that the matrices that we have on the left, they've been hit with this v and are now much smaller than they were before. So rather than having nx by nx matrices here, I've got nr times nr matrices. So I have to pick v, and then I have to solve this problem to get y. But of course I don't know what nr is before I start, so we're not going to do this in a one-off approach, we're going to do this adaptively. So we're going to start with an initial approximation for v, which will just have one vector in it, and then iteratively we will add things to this, this v. So I guess this is the key line, right? This is where all the science is, if I can say that. At each step, we're going to add in at most m new candidate vectors. Remember, m is the number of parameters I've got. This is why I needed m to be fixed in this algorithm. The vectors are essentially going to involve solves, but these solves are finite element solves. So all the algorithm does is solve finite element problems. My basis vectors are solutions to deterministic problems, but they're not corresponding to different samples of my parametric inputs. They are solutions to shifted preconditioned systems, if I can say that. Right? So you can ask me later how to pick SK. So I solve m problems. I've got m candidate basis vectors to add to my basis v. I'll do a singular value decomposition with those m vectors, and I'll pick the most important ones. I'll then, once I've got v, find y, and then I'll return, right? I'll return these two factors. Okay, so you see I'm running out of time. But remember, if we use the standard iterative method, this is the memory that I would need. This is the memory that I now need. Okay? So I'll show you some results. Start with the elliptic PDE. So I have a very fine finite element space here. Here's my diffusion coefficient. It has coefficients that decay very quickly. Very quickly. So I'm cheating here in some sense because I know when these coefficients decay very, very, very quickly, that's when I will have a solution with a very, very, very low rank. That's where you get the best out of these methods. Okay, so here's a problem where I've got 16 parameters, and if you just read this line, so at this stage I've got an enormous polynomial approximation space, which may be far too rich, actually, for what I need, but it's big. So if I multiply these two together, I've got 1.3 billion equations. There's no way I can use a standard iterative solver. But with the algorithm I just outlined, it takes 15 iterations. It builds V so that it has 117 columns. So all I needed to do was solve 117 deterministic PDE problems, and I did that in a couple of minutes. So for the tolerance that I set, and this is the tolerance on the solution of the discrete problem, I can solve 1.3 billion equations in a couple of minutes. Sounds really good. Right? But this problem has a lot of structure, and it is of low rank, and that's why it works so well. Okay, how do we control convergence? Well, we can't control residuals here. If we wanted to compute residuals with respect to the full Galerkin system, we run out of memory again. So unfortunately, when it comes to controlling the convergence, we can really only do it cheaply using this kind of criteria, the sort of differences in successive iterates. This is just to show you the convergence is independent of the spatial discretization because we've built this preconditioning in. Slightly different example, again it's elliptic PDE, but here the terms are decaying more slowly. So this is just to show that when the terms decay more slowly, same story, you'll be out of memory if you use a standard method. If you use the method I just talked about, it'll take 10 iterations, it builds a basis, but NR is now larger. It's larger because of this condition. Coefficients are different, their properties are different, you'll need a bigger basis, a bigger value of NR to meet the same threshold. But ultimately you can solve very, very large problems, more than 500 million equations in a couple of minutes. And then just to show you something that's not an elliptic PDE, right? So this is a system of equations where you've got two solution variables. But again, when you apply the stochastic Galerkin method, you get these linear algebra systems. So this time you have one of the blocks. Looks a bit like what we had for the elliptic problem, but you've got some other stuff as well. The matrix is not symmetric and positive definite anymore, it's indefinite. So the algorithm I've just outlined, in principle it works the same, but there are a few things that you have to change. The story is the same. You can't use standard iterative methods like min-res, but with a method like this you can again solve very large problems in a couple of minutes. And again, the size of NR is determined by the algorithm itself. Okay? So that was a bit quick, but if you want to know more about this particular method, this appeared, it says 2017, but actually it was more like 2015 when it was submitted, so it feels like it's quite old to me. So you can read that paper if you want. If you want to know more about what we've done more recently, then check out my webpage, or just find me next week if you're still around next week, or send me an email. I'll stop there.
Time for a few questions before our morning coffee. Please.
So how do you solve the projected small matrix equation?
Good question, right? So I said I just have to solve PDE solves. It really depends how small it is. So actually, the projected small equation looks like this. So of course you can rewrite this as a Kronecker system, right? And if these are very small, right, you can toggle between, how big is NR? So if NR is very small, you can do it even with a direct solver if it's teeny tiny. If not, you then do it with another iterative method. So we typically do this with iterative methods. So we do another iterative. So there's another inner iteration which will have to happen here. And you'll need to be smart about how you choose your tolerances with respect to the outer tolerance.
Yeah, that's what I would ask next. If you use an iterative method for this, then you make an error. And do you have any idea how small this error has to be?
Well, it's a standard inner-outer iteration thing. So typically we use a dynamically decreasing tolerance for the inner iteration. What you do is you track the accuracy of your outer iterate, and then you choose a tolerance for this, which is a couple of orders of magnitude smaller than the tolerance for your outer iterate, and you do it that way. So, it's clear on the first few outer iterations you wouldn't need to solve this very accurately, but as you are getting later in your algorithm, you want to be solving that more accurately the further you get into the outer iteration, for sure. You can find some statistics for the problems that I say statistics, results. For the problems I've just talked about in the paper, we report numbers of inner iterations and all of that kind of thing. When I've done some experiments with these elliptic problems myself, I haven't seen a big difference. That didn't seem to be the... As I said, as long as it's dynamically decreasing, I think you get something that's sensible. You shouldn't just fix it to 10 to the minus 2 with no consideration about what the accuracy of the outer iteration is.
Questions? If not, I would like to thank again Catherine for this talk.